central region. These are quite numerous, about 30% of our sample. These are objects which we call collimated lobe beds. So we see collimated lobe beds, you don't see the central benching end. And these are presumably objects which have evolved from the bipolar class. This is the multipolar class. You see two or more pairs of diametrically opposed lobes in the objects. The lobes are generally, but not always, distributed in a point-symmetric manner around the center. This is the primary class elongated. I don't call it elliptical because it's not clear. Geometrically, these are really elliptical. And in many of them, the problem is that they are distant, not well resolved, and they, in fact, either because of that or because of projection effects, they in fact be bipolar or collimated lobe objects. And the other problem is that the action of the fast wind during the planetary nebula phase and the fading of the lobes relative to the waste may in fact produce the following morphological evolution pattern. It goes from bipolar class to the lobe class to the bipolar class. This is a very rare class of objects, round objects, surprise, surprise. And there's another small subclass of objects.
After really round, go back.
Sorry? Go
After
back?
really round, my scene is not well. Go back to the round one.
Go back.
Did you check if they are really round, low, left?
This one?
Yeah, it's not bad.
Well, yeah, you're right. There are things which are sticking out here, but you have to define some criteria. And the criteria is that the white shell should have less than 10% difference from the geometry of the round shape. So, yes. So again, whenever you look at round or elongated shapes, you're always worried about, well, could these be projection effects, etc., etc. So generally, you can't convert intrinsically bipolar object. You can't convert intrinsically round object to bipolar or multipolar object, but vice versa is true. So therefore, the important thing to realize is that aspherical objects, whenever we measure the fractions, they're really low in x. Okay, here's another class which may be a subclass of the others, but anyways, there's very, very prominent spiral arms, and we decided to put them as a separate class. So here is I'm not going to go through the scheme in great detail because there's not enough time. Here are the primary classes. The red ones are the ones which we have introduced for young planetary. The black ones are the ones everywhere which existed already from the pre-planetary survey. And we can understand the differences in terms of the pre-planetary sample being smaller, therefore the rare classes don't show up so easily. As well as I mentioned before, the action of the very fast wind from the center star of the planetary, which then further hydrodynamically affects the pre-existing aspherical structure. The scheme is quite comprehensive. We tested that by applying that to a new sample of planetary nebulae which became available during the course of this work by Stanley and Shaw, and we found that we did not need anything new to describe this sample. The secondary classifications are also very important. In fact, the inner bubbles which I mentioned again are most probably those shocks. We see faint inner bubbles in the center of many of these objects. Point symmetry is one of the most important secondary descriptors, and point symmetry again is not a morphological class. It occurs in most of these classes as well, and the different kinds of point symmetry are labeled these. You can have point symmetry because you have point symmetry in particular lobes. You can have point symmetry because the overall shape is point symmetric. You can have various secondary structures which have point symmetric shapes, like the barrel shaped central regions, for example. The inner bubble itself can have point symmetry. The torus itself can be also point symmetric. So there's a lot of different ways that you can have point symmetry. So these we of course we don't want to bias our morphological description scheme by putting in preconceived ideas about what makes these things happen. So the morphological scheme stands on its own. The idea is that you look at the morphological classification and then from there decide what is the theory which applies to it. However, it's quite clear that things like point symmetry do imply secular trends such as recession or wobble orientation of the central engine or outflow. The ANSI suggests the impact of jets on very highly pollinated jets on slowly quiet winds, and the waste clearly implies an equatorial outflow and or this. Note, of course, that the bipolar, multipolar, and low fraction of the membranes belong to this category is very high. It's 55% is measured in sampling, of course, can be larger because of projection effects. Now, I only have one slide, and a lot of ground-based observers may feel slighted about it, but that's the point is, I don't want to offend anybody else, don't have enough time. I do want to mention that an amazing amount of work has been done because, and we've learned a lot because of the various ground-based surveys. And these surveys, you know, probably know the names of all of these, so I can mention, I just want to mention this is kind of cute. For deep sky hunters, where most amateur astronomers use the digital sky survey to identify major candidates, send it off to professional observers, and do HFI imaging. And so this is actually quite productive. So there are huge advantages, of course, over HST, for example. There's a much larger number of objects, so much better statistics, especially for the rare class and the ground class. And so, of course, the ground-based surveys are very good at finding rare objects. And of course, these rare objects, in addition to our people, also include nebulae with binary central stars, which show direct evidence of mass transfer. For example, there's an object discovered and mentioned this paper, the Brennan-Shalsky et al., N2-339, which is a barium central star. And of course, the barium central star indicates which is a product of mass capture from AGB star. Directly shows that mass transfers occurred in the binary effect. So, of course, it produces a lot of interesting objects which are more amenable for detailed study because they are larger. And of course, I would run out of space, so I mentioned all the references here. The disadvantage is that the lower angular resolution, typically 1 arc second from the ground, means that the young battery nebulae cannot be resolved. As I've already shown, young battery nebulae is where the action is clearest. For older planetary nebulae, the extended lobes tend to get fainter, the waist gets slightly extended, and so you may actually be losing bipolar, multipolar objects, resulting in misclassifications, somewhat incorrect statistics, etc. Now, continuing with ground-based surveys, pre-planetary nebulae, the mid-infrared has been amazingly wonderful in this. There was a survey by Eric Lagadek of 85 AGB close to 3 objects. There was a breakup of those, 62 pre-planetary nebulae. And this is an example of the beautiful images that you can get from this. This is a water fountain nebula. I won't have time to describe these objects, but these are very, very important objects for understanding this very early phase of post-nuclear evolution. This object, in fact, also has a synchrotron jet, which clearly shows the presence of magnetic fields. So all the result pre-planetary nebulae, 28 out of this list of 62, departed from our historical. Granular resolution, of course, is not as good as HST, and the images are usually decoupled. So that introduces some uncertainty into the fidelity of the structure that you see. How do you do this? 40 left. Okay. So, out of 40. Okay, AGB set of Serrano. So the millimeter wave and the optical has been quite helpful in showing the morphologies. The mass flow envelopes are generally round. Of course, there are some asymmetries, but they are not as extreme as in the pre-planetary nebula phase. The optical has also helped us a lot. There's a nice survey paper by Maurer and Huggins where they're looking for evidence of a hidden binary at the center in terms of large-scale morphology. In fact, we do find evidence of that. So, now I'm going to read everybody. So, here's a picture of AGB mass loss where the extended circumstellar structure shows signature of a hidden binary at the center. You see these beautiful circular arcs, which are probably spiral structures, and these are caused by the presence of binary at the center. This is a CIT6, a DLA image. This is AGM3068, which is a Hubble image. Here's a nice simulation, which I'm sure we show again. And here's the central binary, what we think of the central binary, the imaging in the thread. There's a lot of asymmetries which are now observed in the extended lobes of the AGB stars, and this is beautiful work by Cox et al. And other people from the MESS program. The Herschel-Pax imaging shows you these extended morphologies. Most of them can be understood by the motion of the AGB star through its stellar medium, like bound shots like this, or objects like this, which they call as eyes, which are somewhat fewer in the sample, just a few, in fact, have central objects or stars which are visual binaries. We don't know, of course, whether they interact with binaries or not. It's quite interesting that I think these morphologies should be examined very carefully, and detailed modeling, which is already done. that should be carried out to see if we can understand if these extended structures have something to tell us about what's at the center of the object itself. I'm going to skip over this, but just mention that H1 observations also become very important with the Nebulae telescope and measuring the very, very extended envelopes, measuring the H1 masses. So this is very important because this gives you both this and the previous extended large-scale structure imaging tells you where the outer limits of this envelope are before it tells you how to determine the total mass which is injected and therefore get a better idea of the intrinsic mass of the central star when it was in the main sequence. Now they are quickly going to run through some interferometric surveys. This is a POSAS study by Arantxa Castro Carrizo, and this is basically showing that the AGB mass was roughly round, but they are asymmetries right in the center. You can see this plot here which shows a gradient in the center position plot. Herschel has also done a very important work, especially from this high-5 pressure program by T.B. Harwell, in showing us what these winds from these PLanetary look like. You have, you can look at submeter far trend lines from CA33 to others, and you can actually see that in some objects, which we know from other data, are young. You see that the winds are warm, CRS 618, 2688, whereas in other objects, which are where the nebulae are older, based on the expansion of this, the winds are cold, and this is simply a cooling of the faster with age. Interferometric surveys are very important. I hope that with ALMA it will be possible to get time to carry out surveys. This is just a survey which is carried out with the old overall array. It's a snapshot survey, so we don't have very, very good imaging observations and imaging fidelity, but we do have, this survey is very important because it helps us find new objects, find new outflows, and in fact find discoveries of extreme objects as well, which are very important for testing our theories. Most of these objects show that the envelope is asymmetric and their velocity gradients. There are broad rings and line profiles in all of them, or 50% of them. So clearly these are post-AGB objects with fast rings, which are distorted shaping the environment around them. Here's one of these extreme objects, IRS 19374, and HST image. You see these very, very wide profiles, about 200 kilometers per second across and more. Here's this one compared to the image from the mid-infrared survey by Eric, and you can see that it doesn't do, it tells you something elongated here in the center. This hourglass shape is about. You can see the hourglass shape in this position velocity. The torus is also expanding, and this object is quite interesting because the total outflow mass at its uncertain estimated distance is about 1 solar mass, which is quite amazing. So now I want to describe you another really extreme object, partly because something which I did, and partly because ALMA has gotten very, very good at observation of this. So this was an object which actually absorbs microwave radiation. The effect is not very surprising, it was predicted. Basically the gas cools adiabatically and eventually can reach a temperature below the microwave band. And so you see the absorption line profile and CO, which are distinct decimation profiles. We observe this with ALMA. Here's an HST image. You see the beautiful hourglass structure. Here's the center. You see a jet-like structure. The ALMA image shows you the same microwave waves here, and you see the line profiles, which clearly show that these are bubble-like structures. At the center, you have a dense waste, and in a moment I'll tell you what this dense waste has. The important thing is the central dusty waste explains why this outer envelope, which is actually really round, appears bipolar in this image, and that is because of preferential illumination. So light can escape from the central disk only around the poles preferentially. Here's a CO120 image. You can see these absorption regions. And another interesting thing is that you see around them patchy emission regions. These are still below the microwave background temperature, but they are hotter than the overall envelope. And these show direct evidence of grain photoelectric heating, which we expected. That was the first direct evidence of that. Here's a profile which shows you what the spectrum looks like. And you in fact see that there's absorption all the way along the linocycle center stop all the way to low velocities. which was surprising at first. It shows that the ultra-cooled shell is expanding radially. It's not constant expansion velocity, and that is actually very important because if you want to produce these bipolar lobes as a result of interaction of fast wind to the outer pole envelope, then the outer pole envelope has to be expanding slower than the fast wind. Now the outer pole envelope is already expanding at 160 km per second, and if you assume that that was true everywhere, then of course this interaction would work. Now, but this spectrum tells us that the absorption effect, that the ultra-cooled shell has low velocities close to the center, and therefore there the fast outflow is able to interact with it, the conductor also presumably is able to interact with it and produce this bipolar lobe structure. Here's the continuum emission, 2.6 mm per millimeters, basically unresolved. And this is the center torus. The interesting thing is that the emissivity index implies very, very large range, it's quite shallow. And that is something which I'll come to. It's not just a phenomenon in this object, but other objects as well. It's something which is completely not understood here. Here's, again, I have to sort of rush through this very interesting work. This is CRL 618. This is, I wanted to show this because I want to show the power of multivariate observations. So this is a beautiful study by Bruce Ballick showing what the proper motion of the knots and the different structures are in this using Hubble images and producing epochs. And they measure proper motion of 0.5 arc seconds, 7 years of existing images. And they have also carried out, together with the phenomenological study, modeling study using high-level models, and the favor of model which is spray of high-speed bullets, in fact, are coming out from the central source and producing these distinct lobes. This is a study which Chinfei Li and I undertake of looking at this object with the SMA with high resolution, less than an arc second, less than an arc second, and we have now begun to resolve these multipolar lobes that you see in optical images. We begin to resolve in CO as well, and that is very helpful because that actually tells us provides very strong constraints on the kinds of models for conventional Ballick presented in this paper. And you can actually measure, using the expansion, you can measure, as Bruce Ballick did with this paper, for the tips of these lobes, you can also measure the expansion ranges for the structures within the lobes. And you find that in fact there have been two episodic events in this. One which occurred about 100 years ago, and the other which occurred about 40 years ago. I think that will be also presented later on by Tifoya. Of the expanding H2 region. So about 40 years ago, the H2 region started expanding from a very small source to a large source. And that's somehow connected with this connected with what is going on in this very interesting multipolar source. So I'm going to just skip this very quickly, but just show you that X-ray emission for planetary nebulae is also a very important way of looking at planetary nebulae, especially because the direct probe of the interaction of the very fast wind with the ejector around them. And this is a lot of work has been done in this field, of course, and I would like to point out that which we will discuss later, this survey called Chan Plans, where it's the first systematic survey of nearby planetary nebulae. Here's this IC418. This is the optical image. This is O3 in the center, and this is the same thing in X-rays, and you can see that the X-rays X-ray bubble corresponds exactly to the O3 bubble. So inner bubbles, I think, are most likely the reverse shocks in these objects, and they glow bright in X-rays. Somewhat maybe unexpected when you look at X-ray emission from planetary nebulae, it's not only that they are probe of the wave-wind interactions, but they also probe processes related to the central star, and maybe related to minority, I don't know what it feels like, or the companion, and negative fields of the companion. I would also like to point out this very nice study which explains why generally the X-ray temperatures are lower than you expect from models. And this is study by Ruiz et al. They demonstrate using pipeline models or 3 pipeline, where they detect the heat conduction layer in oxygen 6 using fused diamond. Okay, so I have 2 minutes left. Okay, so now I'm coming towards the center to the object, and I want to mention this study of what I'm calling class stars called FUV AGB stars. So these are just AGB stars with FUV excesses. And if you actually see AGB star with FUV emission, it's bound to be an excess because the AGB star is a 3,500 star with everything. And so this is so we search for variety using FEV emission AGB stars using the Galaxy archive and our own geo data, and found that large variable UV flux is present in many objects. And we think that's most likely related to radiation activity in the binary. Here's one of our prime objects called Y10, which is otherwise it's just a run-of-the-mill star and a spectral type star. It has this very sharply decreasing FUV and UV fluxes. Here, this is just a SCB of the spectrum showing this radial star, nothing different about the sector star, so and here's a CO line deflection, very narrow line define, which is likely comes from a disk-like torus-like structure. We have carried out a survey of many such objects, and other objects in this sample do show outflows. So it's not that specific objects produce disk-like structures or outflows. You have FUV, AGB stars and centers of both kinds of objects. This is presumably a progenitor of the DP AGB objects I mentioned earlier. So I think this is probably the last thing I'm going to be able to cover. So I wanted to talk a little bit about dust equatorial disks. We know already that there are two types. There are these large tori, which you see just in our images, and you see these medium-sized disks, which are difficult to see otherwise.